Раз. Как там звук есть? Вы как-то проверяете это, да, там? Да? Ну, хорошо. Okay, so at the end of the previous lecture, we stated the Hilbert-Schmidt theorem about compact self-adjoint operators on a Hilbert space. So here is the statement. Suppose that we have a compact self-adjoint operator T on a Hilbert space H. Then there exists a most countable orthonormal family in our space, which consists of eigenvectors for our operator with non-zero real eigenvalues, so that this equality holds. Also, the orthogonal complement of this family is precisely the kernel of T. So this means that informally our operator can be represented by the following picture. So this block corresponds to the subspace span, the closure of the linear span of our family, of our orthogonal family. And this block corresponds to the orthogonal complement, where our operator is 0. Also, the respective family of eigenvalues is precisely the set of all non-zero eigenvalues. That is, the point spectrum of T minus 0. And moreover, every point, every non-zero eigenvalue appears in this sequence, in this family, as many times as the multiplicity of the respective eigenvalue is. And this multiplicity is finite. The multiplicity is finite. Part 5 states that if we have a countable family of eigenvalues, then the respective sequence converges to 0. And finally, we have the following useful formula, which is the so-called Hilbert-Schmidt decomposition of our operator. Okay, so this is the statement, and let's now try to prove this result. Before we prove it, let's recall one more proposition, which was proved at the end of the previous lecture. The proposition states that for each compact self-adjoint operator T on a Hilbert space H, we have the following useful formula for the norm. The norm of T is the maximum of the absolute values of the eigenvalues. This is quite useful. Actually, we will use only a special case of this formula, which states that if this is 0, that is, if we have no non-zero eigenvalues, then the operator is 0. Okay, so let's now prove the Hilbert-Schmidt theorem. For each complex number lambda, let's denote by H lambda the respective eigenspace. Formally, this makes sense for any complex number, but we remember that actually the spectrum is real, so this is non-trivial only if lambda is real. And let's also recall that we already know that the eigenspaces corresponding to distinct eigenvalues are orthogonal. These spaces are orthogonal. This is true for any self-adjoint operator, not necessarily compact. Okay, let's now denote by L the closure of the algebraic sum of all the H lambdas corresponding to non-zero eigenvalues lambda. And of course, this is non-trivial only if lambda belongs to the point spectrum, just by the definition of the point spectrum. So lambda here runs over the point spectrum minus 0. Now for each lambda, let's choose an orthonormal basis. for each lambda in this set, the point spectrum minus 0, let B lambda be an orthonormal basis of H lambda. And let B denote the union of B lambda, where lambda runs over the same set, that is the point spectrum minus 0. Well, then it's clear from this construction that B is an orthonormal basis of L. An orthonormal basis is a total orthonormal family, an orthonormal family whose linear span is dense in this space. So this really implies that B, since each B lambda is total in H lambda, this implies that B is total in L. So it's an orthonormal basis of L. Let's now recall some results on compact operators that were proved at the previous lecture. So we already know, first of all, that each H lambda is finite dimensional. For each non-zero lambda, H lambda is finite dimensional. This is true for any compact operator, not necessarily self-adjoint, and not necessarily on a Hilbert space. So for any compact operator on a Banach space, the eigenspaces corresponding to non-zero eigenvalues are finite dimensional. So this implies that each B lambda is finite. B lambda is finite. And also we know, again, this is true for any compact operator, that the point spectrum is at most countable. The point spectrum is at most countable. And so when we look at the definition of B, we conclude that B is at most countable, because here we have an at most countable union of finite sets. So this implies that B is at most countable. So let's write B explicitly. So let's denote the elements of B by EI, where the index set I is either the natural numbers, if it is infinite, or the finite set from 1 to n, or potentially it can be empty. If there are no non-zero eigenvalues, then I is empty. Well, then by construction, we have the following equation. So the following equality, TEI equals lambda I EI, where each lambda I is a non-zero real number. It is non-zero by construction, and it is real because the spectrum of a self-adjoint operator is real. Okay, so this completes the proof of part 1, which is quite easy. What is essential here is part 2. So we have to show that T is trivial on the orthogonal complement. Okay. First of all, it's clear from the construction that L is T invariant. For the simple reason that each H lambda is T invariant. So L is T invariant. This implies that the orthogonal complement is also T invariant. This was also proved at the previous lecture. If you have a self-adjoint operator, then the orthogonal complement of an invariant subspace is invariant. So the orthogonal complement is T invariant. If we look at the point spectrum of the restriction of T to the orthogonal complement, we see that this is 0. Or more exactly, this is either 0 or empty. Just by construction. by construction, all eigenvectors corresponding to non-zero eigenvalues are here. So, if we restrict T to the orthogonal complement, then this restriction has no non-zero eigenvalues. And now we apply this proposition. So the restriction of T to L orthogonal is also compact and self-adjoint. So if we apply this proposition to the restriction of T to L orthogonal, we conclude that the right-hand side is 0, because we have no non-zero eigenvalues, and so the left-hand side is also 0. And this, as a result, we see that this operator, T restricted to L orthogonal, is 0 by the previous proposition. And this implies that L orthogonal is contained in the kernel. The orthogonal complement of L is contained in the kernel of T. To prove the opposite inclusion, let's take any element x in the kernel and observe that, well, T of x is 0, so the inner product of Tx and EI is also 0. It is 0. Now, since T is self-adjoint, we can move T from here to here. So this is the inner product of x and TEI. But TEI is lambda IEI. So this can be written as follows. And this is 0. So since lambda I is non-zero eigenvalue, we conclude that x is orthogonal to EI for each I. And so the kernel of T is exactly the orthogonal, is contained in the orthogonal complement of L. And together with the opposite inclusion, this completes the proof of part 2. Okay. If we now look at our construction of the spaces H lambda and the vectors EI, we see that properties 3 and 4 immediately follow from our construction. 3 and 4 are true by construction. So for each non-zero eigenvalue, we have chosen an orthonormal basis in the respective eigenspace. So this implies that actually the set of the eigenvalues lambda I is precisely the set of all non-zero eigenvalues. And this is property 3. And by property 4 means follows from the fact that for each lambda, the cardinality of B lambda is exactly the dimension of H lambda, because it is a basis of H lambda. It is finite, and it's exactly the basis of H lambda. So this is finite, as we have already observed, and we have this equality. Okay, now property 5. Property 5. Well, let's suppose that suppose this is not the case. Suppose that lambda I doesn't converge to 0. Then we can always choose a subsequence. There is a subsequence, say lambda ik, such that this subsequence converges to a non-zero number mu. And necessarily mu belongs to the spectrum, because the spectrum is closed. Well, formally we do it in two steps. First of all, since lambda I doesn't converge to 0, we choose a subsequence which is bounded away from 0, just by the definition of the limit such as a subsequence exists. And then we choose a subsequence of this subsequence which converges. Because it is bounded, we can always find a convergent subsequence. And we denote it by lambda ik. So it converges to a non-zero number mu. And let's also observe that this subsequence doesn't stabilize. This follows from property 4. This subsequence lambda ik doesn't stabilize because this is finite. So each each number in the sequence appears only finitely many times. So it doesn't stabilize. This implies that mu is not an isolated point on the spectrum. Mu is not an isolated point. Of the spectrum. And this is a contradiction. At the previous lecture, we proved that for each compact operator on the Banach space, each non-zero point in the spectrum is isolated and actually is an eigenvalue of finite multiplicity. So this is a contradiction. And the contradiction completes the proof of 5. So this implies that actually lambda I goes to 0. And finally, the Hilbert-Schmidt decomposition, part 6. To prove formula 6, let's observe that if we take a point in our space, label x, then of course t of x belongs to the image of t. This is clear. And the image is contained in the closure of the image. But we have observed at the previous lecture that for any operator t, for any bounded operator t on the Hilbert space, the closure of the image is nothing but the kernel of t star, of the joint operator. This is true for any bounded linear operator on a Hilbert space. But t is self-adjoint. T is self-adjoint, so this is just the kernel of t. And the kernel of t so this is I forgot to put the orthogonal complement here, sorry. So the image of t is of the closure of the image of t is the orthogonal complement, of course, sorry. The orthogonal complement of the kernel of t. The orthogonal complement of the kernel of t. And this orthogonal complement, if we look here, if we take the orthogonal complement here, we see that this is the double orthogonal complement of this family. That is the closure of the linear span. The closure of the linear span of the family EI. Okay, so the vector t of x belongs to this closure of the linear span. So we can decompose the vector t of x with respect to this orthonormal basis. So EI is the orthonormal basis of this subspace. So we can decompose t of x in the following form. This is the sum of its Fourier series. And now we again use the assumption that t is self-adjoint and move t from here to here. But t of EI is lambda I. And as a result, what we get is exactly the Hilbert-Schmidt decomposition. And this completes the proof. Okay, so roughly the Hilbert-Schmidt theorem means that each compact self-adjoint operator on the Hilbert space is diagonalizable, in the sense that it is diagonal on some closed vector subspace and is zero on the orthogonal complement. And actually, if H is separable, then we can extend this a little bit and choose a countable orthonormal family, a countable orthonormal basis in the kernel of T. And if we write the matrix of T with respect to this extended basis of H, then it will be diagonal. So this is the picture which describes the structure of a compact self-adjoint operator. Now, a natural question is, can we extend this result to non-compact self-adjoint operators? Of course, the self-adjointness is essential. Already, if we have a two-dimensional space, a finite dimensional space, we can easily construct a non-self-adjoint operator which has no non-zero eigenvalues. So such an operator is not diagonalizable. But how about the compactness? Well, actually, there are simple examples which show that the compactness assumption is also essential. Here's a simple example and an exercise at the same time. So let H be the Big-L2 space over the closed unit interval, and let T be the operator on H, which acts as the multiplication by the coordinate. Tf of S equals Sf of S. Then it's easy to show that this operator is self-adjoint, but the point spectrum is empty. So this operator has no eigenvalues at all. And so this implies that the Hilbert-Schmidt theorem doesn't hold for non-compact self-adjoint operators. If you try to extend the Hilbert-Schmidt literally to non-compact operators, then the result is false. But fortunately, there is a suitable modification, or rather, just a restatement of the Hilbert-Schmidt theorem, which can be extended to arbitrary self-adjoint operators, not necessarily compact. And the respective result is probably one of the most famous results in the classical operator theory. It is called the spectral theorem, and we will prove it in the end of our course. Okay, now our next strategic goal is to come back to Fredholm operators between arbitrary Banach spaces and to study some useful properties of Fredholm operators and of their index with the help of the Ries-Schauder theory. But before we can do it, let's make a short digression into the theory of Banach spaces, and let's discuss topological direct sums. Topological direct sums and complemented subspaces. So first of all, let's introduce a simple and useful construction. So suppose we have two normed spaces, x0 and x1, and the real number p greater than or equal to 1, and possibly equal to infinity. And we define the LP direct sum of x0 and x1 as follows. So this is a normed space denoted like this. And it is defined as follows. As a vector space, this is just the direct sum of x0 and x1. And we equip the direct sum with a norm. So the norm is given by the following formula. So an element of the direct sum is just an ordered pair, x0, x1. So if p is finite, then this norm is given by the following formula. If p is finite. And if p is equal to infinity, we take the maximum of the norms. Actually, we have already used this notion in the case where p equals infinity. So this is the LP direct sum. It's a simple exercise. Well, formally, all these norms are not the same, but it's a very easy exercise to show that they are equivalent. These norms are equivalent to each other, and they determine the product topology on the direct sum. Okay. Now let's suppose that x0 and x1 are vector subspaces of a bigger normed space X. Suppose now that X is a normed space, and that x0 and x1 are vector subspaces of X. We say that X is the topological direct sum of x0 and x1, and we use the following notation. If the following operator, which acts from the L1 direct sum of x0 and x1 to X, and takes each pair of vectors, little x0 and little x1, to their sum. So this operator is a topological isomorphism. In this case, we say that X is the topological direct sum of x0 and x1. Of course, because of this exercise, we see that we can easily replace here the L1 direct sum by LP direct sum for any p. The L1 direct sum can be replaced by the LP direct sum for each p. So I've chosen the L1 direct sum just for technical convenience. This is not essential here. By the way, first of all, if we look again at this operator, let's observe that this operator is always bounded just by the triangle inequality. The norm of this vector, the norm of the sum, is less than or equal to the sum of the norms. And let's also observe that this operator is a vector space isomorphism, if and only if X is the algebraic direct sum of x0 and x1. But here we need the stronger condition that it is a topological isomorphism. Let's also observe that the fact that this operator is a topological isomorphism can be explicitly written as follows. So X is the topological direct sum of x0 and x1, even only if, first of all, X is the algebraic direct sum of x0 and x1. And second, this is property 1. And second, property 2, there is a constant, a positive constant c, such that we have the following inequality. The sum of the norms, little x0 plus little x1, is less than or equal to c times the norm of their sum. Actually, we don't need brackets here. And this holds for any little x0 in the first subspace and little x1 in the second subspace. So it kind of converse to the triangle inequality holds. Well, indeed, property 1 means precisely that this map is a vector space isomorphism. And property 2 means exactly that the inverse of this map is bounded. So it is a topological isomorphism. Okay, let's now prove some simple properties of topological direct sums. Proposition 1. Suppose that we have two normed spaces, x and y, and such that x is the topological direct sum of vector subspaces x1, x0 and x1. And suppose that we have a linear operator t from x to y, which is not assumed to be bounded from the very beginning, just a linear operator. I claim that t is bounded if and only if the restrictions of t to these summands x0 and x1 are bounded. Well, of course, the left to right application is trivial. The restriction of a bounded operator is always bounded. So we have to prove the right to left implication. And this is also very easy because if we take again a pair of vectors in the first summand and in the second summand and apply t to their sum, so this is tx0 plus tx1. By the triangle inequality you have the following expression. Now, because the restrictions of t to the subspaces x0 and x1 are bounded, we can estimate this as a constant, a certain constant c prime times the sum of the norms, where c prime is just the maximum of the norms of these two operators. And then combine this with our assumption that we have the topological direct sum. So we have this inequality. And that's it. As a result, we see that t is bounded. The notion of a topological direct sum can be conveniently interpreted in terms of bounded projections. So first of all, let's try to understand what a projection is in a general case. Well, let's recall the following simple fact from linear algebra. This is proposition 2. Suppose that X is a vector space and P is a linear operator from X to itself. Then the following conditions are equivalent. Condition 1, P squared equals P, because P is idempotent. And condition 2, there exists vector subspaces x0 and x1 in X such that X is the direct sum of x0 and x1, and such that P restricted to x0 is the identity map and P restricted to x1 is 0. And moreover, so conditions 1 and 2 are equivalent, and moreover, if the subspaces x0 and x1 are as above, are as in 2, then x0 is nothing but the image of P, and x1 is nothing but the kernel of P. Well, the proof is a simple exercise in linear algebra. Probably you are already familiar with this result. And let's give the following definition. Such an operator P, which satisfies any of these two equivalent conditions, is called the projection of X onto x0 along x1. Such an operator P is called the projection onto x1, onto x0 along x1. In this context, in Russian, projection is проектор. A little Russian digression. Значит, когда мы говорим про образ вектора под действием некоторого проектора, то образ вектора называется проекцией вектора на подпространство, а сам оператор называется проектором. Но по-английски нет разницы, мы в обоих случаях говорим projection. A simple but useful observation is that if I have a projection P, if P is a projection onto x0 along x1, then 1 minus P. 1 minus P is also the projection onto x1 along x0. The projection, of course, it is uniquely determined by the subspaces. Well, this is immediate just from this property. If we replace here P by 1 minus P, we see that 1 minus P is 0 on the first subspace, and 1 minus P is 1 on the second subspace. Okay, now we can easily characterize topological direct sums in terms of projections. This is proposition 3. This is 1, 2, 3. So suppose that X is a norm space. x0 and x1 are vector subspaces of X such that X is their algebraic direct sum. then the following conditions are equivalent. Condition 1, x is the topological direct sum of x0 and x1. Condition 2, the projection onto x0 along x1 is bounded. And condition 3 is symmetric to condition 2. The projection onto x1 along x0 is bounded. Well, first of all, let's observe that conditions 2 and 3 are obviously equivalent because of this observation. Of course, P is bounded if and only if 1 minus P is bounded. Well, 1 implies 2. Suppose that x is a topological direct sum. Let's show that the respective projection is bounded. So let P denote our projection. Note the projection onto x0 along x1. So P applied to little x0 plus little x1 is just x0. Well, as above, little x0 belongs to the first space and little x1 to the second space. And of course, the norm of x0 is less than the norm of x0 plus the norm of x1. But we have this inequality. And that's it. So we see that P is bounded. Or, by the way, it would be just easier to refer to proposition 1, because P is bounded, clearly bounded on x0, and P is bounded on x1. Okay, and finally, let's show that 2 implies 1. 2 implies 1. So let's look once again at this operator, which appears in the definition of the topological direct sum. Well, let's denote it by sigma. Let's denote it by sigma. And let's observe that the inverse of this map, the inverse of sigma, which exists because x is assumed to be the algebraic direct sum. So sigma is bijective. And the inverse of this map is given by the following simple formula. It takes each element x to the pair p of x and 1 minus p of x. And we see that since p is bounded, this operator is also bounded. And this completes the proof. As a corollary, we see that if x is the topological direct sum of x0 and x1, then both the subspaces x0 and x1 are necessarily closed. If x is the topological direct sum of x0 and x1, then x0 and x1 are closed in X. For the simple reason that they are the kernels of the respective projections. X1 is the kernel of P, where P is, as in the proof of the previous result, and x0 is the kernel of 1 minus P. And the kernel of a bounded linear operator is always closed. By the way, there is a special case in which the converse is also true. Proposition 4. If X is a Banach space, and if x0 and x1 are closed vector subspaces, such that X is their algebraic direct sum, then X is their topological direct sum. To prove this result, we simply apply the Banach inverse mapping theorem. We apply the inverse mapping theorem to the same operator sigma between the L1 direct sum and X. So it is bijective because X is the algebraic direct sum. It is obviously bounded. And all these spaces are Banach spaces. X is a Banach space. X0 and X1 are also Banach spaces because they are closed subspaces of X. And it's easy to see that the L1 direct sum of two Banach spaces is also a Banach space. So it is a bijective bounded linear operator between Banach spaces. And by the inverse mapping theorem, it is a topological isomorphism. Okay, let's now consider the following problem. Suppose we have a Banach space X and the closed vector subspace X0. Can we always find a subspace X1 such that this formula holds? There is a special name for this situation. If this is indeed the case, then we say that X0 is complemented in X. So we give the following definition. Suppose that X is a normed space, and X0 is a vector subspace of X. We say that X0 is complemented in X if there exists a vector subspace X1 in X such that X is their topological direct sum. There is an obvious necessary condition. It follows from this corollary. This corollary implies that a complemented subspace is necessarily closed. Complemented subspace is closed. This follows from this corollary. In some special cases, the converse is also true, which looks very natural. Here is a simple but important example. If we take a Hilbert space, if H is a Hilbert space, and if we take any closed subspace, then it is complemented. Every closed subspace H0 of H is complemented. Because we have the orthogonal complement theorem. Because H is the direct sum of H0 and H0 orthogonal. And this is actually the topological direct sum. It is topological either by proposition 4, but there is another obvious way to see that this is a topological direct sum because it is isometrically isomorphic to the L2 direct sum by the Pythagorean theorem. So we conclude that H0 is complemented in H. Surprisingly, it turns out that this result doesn't extend to arbitrary Banach spaces. And here is probably the simplest counterexample, which is an exercise at the same time. And the exercise is not entirely trivial. It is given at the end of the second exercise sheet. Namely, little c0, the space of sequences that vanish at infinity, is not complemented in L infinity. In L infinity. This is not entirely obvious, but anyway, this is probably the simplest counterexample, the simplest example of a non-complemented subspace. And actually, this is not a pathology. It turns out that non-complemented subspaces exist, and they exist in abundance because of the following result, which I state without proof. This is a theorem due to Lindenstrauss and Zafriri. (1971). Suppose that X is a Banach space, and suppose that each closed vector subspace of X is complemented. Then X is topologically isomorphic to a Hilbert space. So in other words, if you take any classical Banach space which is not isomorphic to Hilbert space, like for example the space of continuous functions on 0, 1 on a closed interval, or the little C0 space, or the little L infinity space, or the little LP space where P is different from 2, or the big LP space where P is different from 2, we can always find a non-complemented subspace. So the existence of non-complemented subspace is a rule. This is not a pathology, but this is a rule for Banach spaces. Okay, let's now prove a useful criterion for complemented subspaces. So we have the following result. Suppose that X is an ordered space, and X0 is a closed vector subspace. Then the following conditions are equivalent. Condition 1, X0 is complemented in X. Condition 2, X0 is the image of a bounded projection. There is a bounded projection, a bounded linear operator, P on X, such that it is a projection, P squared equals P, and such that X0 is the image of P. And condition 3, there exists a bounded linear operator S from the quotient of X modulo X0 to X, which is a section for the quotient map, such that Q composed with X is the identity map of the quotient. And here Q denotes the quotient map. Q is the quotient map from X to X0. Okay, so first of all, the equivalence between 1 and 2 is actually immediate from proposition, I forgot the number, from the probably that was proposition 3, where the statement was that if we have an algebraic direct sum, then this direct sum is a topological direct sum, if and only if the respective projection onto x0 along x1 is bounded. Probably this is proposition 3. So this follows from proposition 3. Indeed, if x0 is complemented, we can write x is the topological direct sum of x0 and x1, and the projection of onto x0 along x1 is bounded. And that's it. And of course, the other way around. If x0 is the image of a bounded projection, then x is the topological direct sum of x0 and the kernel of P. Let's now show that 2 and 3 are equivalent. First, we show that 2 implies 3. To construct Q, we consider the following picture. We consider the operator 1 minus P, where P is satisfies condition 2. So P is the identity map on its image because it's the projection onto x0. So 1 minus P vanishes at x0. And so 1 minus P factorizes through the quotient. So there exists a bounded linear operator S from here to here such that the diagram commutes. Well, so this means that SQ is 1 minus P. If we multiply this on the left by Q, we see that QSQ equals Q minus QP. But QP is 0 because P is the projection onto x0 and Q vanishes at x0. So this is just Q. QSQ equals Q. And finally, we can cancel Q on the right, because Q is surjective. So a surjective operator, a surjective map can be cancelled on the right. And we conclude that QS is 1. Okay, so this shows that property 3 holds. And finally, let's show that 3 implies 2. So we have to construct a bounded projection onto x0. And actually, the proof of the previous implication suggests the formula for P. P, let's denote by P 1 minus SQ. So we have to show that this is a projection onto x0. Well, first of all, SQ squared. What is this? SQ. But since QS is 1, we conclude that this is just SQ. So SQ is a projection, and P is 1 minus SQ. So this implies that P is also a projection. How about the image of P? Well, the image of P is the kernel of SQ. So what is the kernel of SQ? So this is the image of P. And the kernel of SQ is the kernel of S. Sorry, the kernel of Q, of course. The kernel of Q, for the simple reason that S is injective. S is injective by this formula. So this formula obviously implies that S is injective. And since S is injective, the composition of SQ has the same kernel as Q. And the kernel of Q is X0, of course. So we see that the image of P is X0. And this completes the proof. So we have constructed a bounded projection onto X0. As a simple corollary of this result, let's show that each finite dimensional subspace is complemented. And each closed subspace of finite codimension is complemented. So these corollaries will be useful in our applications to Fredholm operators. So corollary one, suppose that X is a normed space, then and suppose that X0 is a finite dimensional vector subspace. Then X0 is complemented. To prove this result, first of all we choose a basis in X0, say E1 to En. And let's take the dual basis of the dual space, F1 to Fn. The dual basis of the dual space. The dual basis means that Fi applied to Ij is the Kronecker delta Ij. Now we apply the Harmonic extension theorem and extend the functionals F1 to Fn to the whole space. And the extensions will be denoted by F1 tilde and Fn tilde respectively. So we get linear bounded linear functionals on X. And now we can explicitly construct the projection onto X0. We define P, an operator P on X, by the following formula. P of X is the sum from 1 to n F tilde of X EI. Fi tilde of X EI. So clearly this is a bounded linear operator because each functional Fi tilde is bounded. Its image is contained in X0. And P is the identity map on X0, because if we substitute here any Ej, we get the identity map. So P takes Ej to itself. So it is the projection, it is a projection onto X0. P is a bounded projection onto X0. Okay, so each finite dimensional subspace is complemented. And corollary 2, if X is a normed space, and suppose that X0 is a closed subspace of finite codimension. Closed subspace of finite codimension, which means that the dimension of the quotient is finite. Then I claim that X0 is complemented. So to prove corollary 2, it will be convenient to use part 3 of the previous theorem, that is to find a continuous section for the quotient map. And this is very easy. So again, we choose the basis of the quotient, E1 to En. This is the basis of the quotient. And for each I, we choose I from 1 to n, we choose a pre-image. For each I from 1 to n, let ei, let xi be an element of x such that q of xi equals ei. And now we define a linear map. A linear map S from the quotient to x by the following formula. So we define it on a basis. It takes each ei to xi. So clearly it is a section for Q. Qs is the identity map just by construction. And this is bounded because the space is finite dimensional. So each linear operator from a finite dimensional normed space to any normed space is bounded. So now part 3, the equivalence between 3 and 1 in this theorem shows that x0 is complemented. Okay, so our next goal will be, so now as I promised, we will come back to Fredholm operators, and our next goal will be to prove a useful criterion for Fredholm operators, which shows a nice relation between Fredholm operators and compact operators. Well, probably we'll not try to do it today because it's a rather long theorem. So we'll prove this result at the next lecture. And then we apply this characterization to the study of the Fredholm index. We will see that the Fredholm index has several nice algebraic and topological properties. And finally, as an illustration, we will show, we will prove an elegant index formula for Toeplitz operators on the unit circle. So this is our plan for the next lecture. And that's all for today. Thank you.